All right, next we need to look at the derivative of the natural logarithm function before we get too much further into working with exponential and logarithmic functions. So if we have a function y equals ln x, we need to know what its derivative is. To find the derivative of this, we are going to change it to a form that we can work with and we're familiar with, and then differentiate implicitly. All right, so what I mean by that is instead of having y equals ln x, if we take anti-log base e on both sides, we just get x equals e to the y. All right, and then if we take the derivative of both sides, that's differentiating implicitly. d dx of that side is d dx of this side. Think about what we're going to get. I'm going to move this up here now. If you take the derivative of this left side here, the derivative of e to the y is e to the y times something else. If it was just e to the x, it would just be e to the x. But since this is something other than just an x, we need to do the derivative of that thing, which is y prime, or dy dx, all right, which is what we're looking for. On the other side, the derivative with respect to x of x is just 1. Now we want to solve for this thing, dy dx or y prime, whichever one you want to call it. You're going to do that by dividing both sides, so you're going to have 1 over e to the y. We can do a substitution here. Substitute for e to the y. What did we have over here? E to the y was x. So we, instead of e to the y, we can write 1 over x. All right, so the derivative of that natural logarithm function is 1 over x. Put it down in this box down here, 1 over x. That's the derivative of the natural logarithm function. So now that we've got that result, let's see what it means when we look at it graphically. So I have something set up here already. We have that function, that's the natural logarithm function. And we have its derivative, which is 1 over x, or x to the negative 1, same thing. And let's move this over, because we'll ignore the other side, because that, even though the derivative graph exists over there, the original graph doesn't exist over there, so it doesn't matter much to us. But the connection we have to make is the same as we always have to make, which is the connection between the slopes of this graph, and we have a point to trace there. So there's a point that traces the slopes of the original graph. The slopes of the original graph are going to be the y values of that derivative graph. So we have another point on there that corresponds to that, and it's going to follow it here. All right, so as you adjust this point, the tangent on the original graph, think about the slopes of that red line and how they match up with the y values of this. All right, so as this line gets steeper and steeper as you get closer to the axis here, this point starts to ramp up because that's the y values there are the slopes, right? If you look over here, the slopes of that red line, 2.35, it's the y values of that point, 2.35. Okay, as this thing drops, or as this slope of this decreases, it's getting less and less, while these things, the values over here decrease, they head towards 0. All right? So that's a look at the derivative of the natural logarithm function, finding out what it is, and then looking at it graphically. Hopefully that helps you understand and be ready to start using it and applying it in other situations.